I'm Sanjay, and I'm here to talk about the effects of time resolution on background model for Neutrinoless double beta decay. I'm working with Dr. Carson Hager on the Wright experiment. So what is Neutrinoless double beta decay? Azia, I think, mentioned about beta decay in her presentation, and so that's when you have a neutron that's hanging out, that it turns into a proton, you get an antineutrino and an electron out of that. Double beta decay is just that happening twice. You multiply everything by 2. And neutrinoless double beta decay is double beta decay, but you don't have any neutrinos. So what that does is it violates lepton number. You get 2 leptons where you had none. And the reason that's interesting is because it gives you more matter than it does antimatter. And so this clues into why there's a matter-antimatter asymmetry in the universe. So the standard model forbids this. This shouldn't happen because it violates lepton number. But there's ways you can calculate decay rates that change your assumptions. And so what that gives you is a half-life of around 10 to the 25 years, and that's a very long time scale. So it's an extremely rare process, and the way you detect that is you have a ton of material and you wait a much shorter amount of time. So you would expect maybe with a ton of material, you see a few decays a month or a year. That's still a pretty rare process, and noise can mess you up. And so what Wright does is it's a bolometry experiment, and you have 988 crystals of tellurium dioxide. And these crystals are both your decay source and the detector itself. And what the crystal does is when a particle strikes it, it heats up. And you have a germanium thermistor that reads thermal energy as a voltage, which you can then convert to this counts as a function of energy. That's your data. You just have voltage over time, and you have a derivative trigger that can pick out the peaks and so catalog all your events. Okay, so multiplicity is an important thing. Now you can imagine that an event happens somewhere in the detector that produces 2 particles that go off in opposite directions and strike 2 different crystals. And the problem with that is you might not know that they come from the same event. It registers as 2 different things. So we call such events coincident. And so the number of crystals they interact with is the multiplicity. It interacts with 2 crystals and 2, and so on. And we would like to classify coincident events together. So here's the polar spectrum. Right there is our region of interest. We'd like to see a peak there to know that neutrinoless double beta decay is a thing that happens. And you can see the counts. This is all the background. And that's a very low background. It's pretty low. You might get a 10 to 100 counts a year, but that's still a lot of noise, and we still don't see neutrinoless double beta decay. And so that either means that it doesn't exist or it's an extremely rare event. So what Wright does at the moment is set lower limits on the half-life of neutrinoless double beta decay, so we know it has to be rarer than that. And what we do is try to cut down on the noise as much as possible. And so part of that effort is the background model, which is where you try to simulate events in the detector and see how they contribute to the background. And so the process is to simulate perhaps events that come from a certain isotope. Do that for every isotope that might give you noise and create a linear combination of that fit that to the background spectrum of the experiment. And part of that is time resolution. So the thing is, a bolometer is a very slow detector, and so you don't have a lot of clear information on when events happen. So suppose an event happens and it strikes a crystal. Crystals might take tens of milliseconds to respond to the actual event. And so if you have an M2 event, so 2 particles strike 2 different crystals, the event itself might have happened maybe nanoseconds apart, but the crystals may respond several milliseconds apart from each other. And so you need to classify them together. And so we do that the only way you can, really, which is you set a coincidence window. So say if you have 2 events that are within 10 milliseconds or 30 milliseconds of each other, you say they are coincident. And then you also apply a radius cut. So if it's too far out, you say these cannot be coincident. If it's close enough, you're good. And that can give you, say, effects on the spectrum. So if you look here, the multiplicity changes as you apply different kinds of time resolution. Should have probably put how many milliseconds that is, but here you can see multiplicity 2 is the most common thing, and there you have like that is drastically reduced just by applying time resolution on your data. And here you can see what it does to the energy spectrum itself. You see like the events over there go down by like a whole order of magnitude. And so that can have drastic effects on how you fit that to the background. And so, here you can see the delta t between the events in multiplicity 2 sort of packages. And the question then is, what is the correct model for adding time resolution? And the way we do it now is to use a Gaussian with varying widths. And so this kind of represents that. And we need to know if it's a Gaussian and what kind of model is correct. And so the program is to look at live data and how time resolution is shown in live data and try to fit that. And so that is part of what is going to be part of my future work. And I hope to present more complete results of this project later this year at the DNP 2025. And so a lot of my work this summer has been very computational and like very straightforward. So I've just gotten simulation data and run the program that adds time resolution to it and made plots. And so you can see the plots here. As far as my methods go, they've been pretty straightforward. So yeah, I hope to have better results later. And so thank you all for listening. And I'd like to thank Ridge Liu, he's in the room, Tyler Johnson, and Dr. Carson Hager for all their help. I'd like to thank Dr. Thomas Gutierrez of Cal Poly, where I'm from, for sending me here. And I'd like to thank the 4A and Cupid collaborations and the NSF for funding my activities.
Yes.
Awesome. So yeah, can you go back to slide 11 where you have the spectrum? So just to make sure I followed on the timing cut. So you're cutting a lot of very high energy events when you apply this timing coincidence. I assume that's because there's really correlated events out there.
Well, it's not that we're cutting the events, it's that what we're doing is once you cluster the events together, you add up their energies, and that's how you get the spectrum. And so it just sort of like moves them around.
It moves them around. Yeah. But that's because there's real events that are physically correlated out in that high energy part of the spectrum. What are the main correlated events out there? Are they cosmogenic, or is this radio, like alpha decays? Because I would think the alphas might only show up in one detector.
Yeah, I'm not sure what the events are necessarily. What I do is just apply the criteria for coincidence, and so that's just, they might be within a certain time window, a certain distance.
Just a comment. I mean, in this part of the spectrum, we are generally dominated by alphas. There is some cosmogenic contributions, but it is the alphas, and I think part of the work in the future will be trying to understand really how that multiplicity cut correlates to.
Yeah. I was wondering, you showed a plot about how the response time of the detector is a little different, and that's where a lot of this timing cut comes from. I was curious if you thought at all about incorporating the timing responses of the different detectors, since you'd presumably know which detectors these are detected in.
I believe that's already been done. I think we have a matrix that just accounts for all that.
Further questions? Seeing none, thank you.